Okay, so we are going to talk about a way to make our life easier. We were able to find the derivative of something in the form like this because it made sense and it wasn't that hard to write this or to expand this and then take the derivative of that. Okay, so it's not difficult to do that. But what happens if it is now going to be f of x is equal to x plus 4 times the square root of x minus 3? Can we expand that? And the answer is no. We are not able to expand that. Right? So what do we do in this case? Right? Well, that's where the product rule is going to come in. It's just another rule. Am I causing you panic attacks?
No, it's so funny.
It's another tool in your toolbox to allow you to do complex derivatives. And we know just by looking at this. What's the derivative of f of x? Dylan, what's the derivative of f of x? 1. The derivative of g of x is 2x. The derivative of h of x is 3x squared. And we can see this, that we can see that if I do f of x times g of x, I'm going to get h of x, right? X times x squared gives me x cubed, very basic. However, f prime of x times g prime of x does not give us h prime of x. Right? What we have here is 2x does not equal to 3x squared. So that shows that this, when we have the multiplication of f times g, it does not equal to f prime of x times g prime of x. Okay? It does not work. So we need to use a formula that we probably would remember, and you probably should write this formula down. Okay? So if you have two functions, both that are differentiable, then f times g is the function. If you want to take the derivative of that product, you are going to go f prime of x times g of x plus g prime of x times f of x. And if you're going to write this in Leibniz notation, I did hand out this damn thing, didn't I? Right, Leibniz notation, this would be d dx of the function f of x times g of x. I'm going to write it. G of x times d dx f of x plus f of x times g times d over dy g of x. Okay. Now, that's just the basically. Now again, there's the rule. Where the heck did this rule come from? Well, it came from a proof. Okay? And I've got most of the proof down here. Okay? So, if we want the derivative of f of x, we apply the definition for that. Copy that down. Now, here's the proof. So we're going to start with our definition. Capital F is the full one. Why I use capital F instead of something else. But here's our definition. F of x plus h minus f of x over h. We defined our function f of x as the product of two functions. So I'm going to replace this here with f of x plus h times g of x plus h. And I'm going to replace this with f of x plus times g of x. So I'm just doing a simple substitution using this. Now I'm going to do a little bit of trickery. I am going to add two terms to that expression that's above. Those two things I just added. Am I allowed to add them? What do they add up to? 0, right? So, bit of a trickery here. I'm going to add these guys, and I'm going to, right, there's a plus sign here, minus sign here. So, these two guys add up to 0. So, we can add 0 to things. We just write in a different thing. Now, what that does is, we're going to do some partial factoring. What's common to the first two terms here? F of x plus h. That leaves me with g of x, that leaves me with g x plus h minus g of x. And I'm going to split the fraction also and put the h underneath there. Okay? What's common to these two terms? And again, I'm going to split the fraction and I'm just going to put it underneath there. Okay? Now, applying our properties of limits, we have the limit of a product. Well, I can write that the product of two limits. So this becomes the limit h approaches 0 of f of x plus h times the limit g x plus h minus g of x over h. And here we have the sum of a limit, so I'm going to perform the same principle here. And you can see why I split the fraction now. What is the limit as h approaches 0 of f of x plus h? Function is f of x. Right? When you take that limit, there's no h. We just go ahead and plug in 0 for our h, and we get f of x. Now, I forgot to write my h approaches 0 here. What is this? Is that not the definition of the derivative of g of x?
All again.
So we have our g prime of x. That entire thing is our definition for the derivative of g prime of g of x. Same thing here. As h approaches 0, well, there's no h in that, so that'll be g of x. And here again, this is the definition of the derivative of f of x.
I thought we were going to do that for every question, and I was like, ooh, that sucks.
No, we're not. We're just going to, this is the proof. So we have now shown that the derivative of the capital function defined by the product of two functions. So a function is a product of two functions. We're going to apply this. This, again, is supposed to be lowercase because my uppercase suck. But there is our product law. Okay. We don't ever have to do, well, maybe I'll ask you to prove it on a quiz or an exam, but mathematics, again, we need to show that it's true for everyone, not just one or two. Well, this, by doing this with no numbers and doing it just with definitions, we've shown it to work for every function that is a product of two other functions. This here, this, what you're saying, where did this come from? This is just our definition of a function, right? Sorry, definition of a derivative. That's what we use. Here we had it for capital F of X, right? That's our definition. We just put G in here. So I can replace this with F prime of X, or in this case down there, G prime of X. Okay. Now, I prefer myself, because the product, or the quotient rule, which is going to be talked about tomorrow, I prefer to have it in this form, where I take the derivative of F of X first. It just reminds me when I do the quotient rule to always take the derivative of the function that we call F first. Doesn't really matter. So if I was to do a question like this one, I would say this function is F of X and this function is G of X. Okay, and this function is H of X. Okay, so that's F of X, that's G of X. Now I happen to really like this notation. I know it's a little bit more here, but we have G of X times d dx of our function F of X plus F of X times d over dx of G of X. So it's just a different way of writing it. It does help me when I start to go ahead and do my, take my derivatives. And I'm going to show you what I mean here. Yes, I'm going to skip a lot of that myself. And I probably should, because I have habits of losing things. But this is a good reminder what I'm doing. So again, am I causing you a panic attack?
This is fantastic. I love this. That was pretty cool, actually.
Okay, so here we have, I want to know the derivative of this function. We have this function, which I'll call F, and I'll call that function G. Okay. I could multiply this out with no problems. It's not terrible. It's a two binomials multiplied together, but it's not necessary. So my derivative, dy over dx, is equal to 2x minus 7 times the derivative of x squared plus 1 plus x squared plus 1 times the derivative of 2x minus 7. Okay, so that's my power rule using my Leibniz notation. This is telling me I have to take the derivative of that. That's why the d over dx of that. So the 2x minus 7 doesn't change. What's the derivative of this? 2x plus the x squared plus 1 doesn't change. And the derivative of 2x minus 7 is 2. Sneeze coming. Or not. No. we're gonna have to multiply this out, so I want to simplify this right in the simplest forms. 4x squared minus 14x plus 2x squared plus 2. And I could also quite easily be happy with you taking this out. Either this term or that term would be considered the simplest form. From here, all it is algebra gather-like terms, write it in your simplest form. Okay. Now, do I have to look at the product rule every time I do it? No, I don't. And I wouldn't expect you guys to either shortly. Why do we got a calculator out for?
I'm just looking at stuff.
Okay. Now, but I do have to look. I do have to look for the quotient rule, which we'll talk about tomorrow, almost every time I do it. Kind of what I've started getting in the habit of doing the product rule the same way as I do my quotient. So in this case, this guy is going to be my first function, f. This guy will be my second function, g. Again, can I multiply that out to start with? Yes, I can. Okay. But I don't want to. I want to get into the habit of using this. Now, I'm going to be a little bit annoying because I'm going to mix up both Leibniz and the Newtonian notation for this. But we have x plus 2 times the derivative of x to the 1/3 plus x to the 1/3 times the derivative of x plus 2. So the x plus 2 stays the same, times 1/3 x to the negative 2/3 plus x to the 1/3 times 1. Now at this point, yes, I don't have a real issue with you expanding this left-hand side here. But what I see is taking out a common factor of 1/3 and taking a common factor of negative 2/3 of it. So I'll take out a 1/3 and x to the negative 2/3. That's going to leave me with x plus 2. And what's going to be left when I take that 1/3 x to the negative 2/3 out of this? I'm going to be left with a 3x. So 1 divided by 1/3 is 3. X to the 1/3 divided by x to the minus 2/3 would be x to the 1/3 subtract negative 2/3. So that's where I got my 3x. And there's the tidier version, okay, for that one. I could, yes, definitely. I could take a 2 out of the top and have 2x plus 1. Okay, so this one type of question here is, where's the function? It's actually under just basically trying to remember if you can think about what the derivatives of a function or a function made up of the product of two other functions. Here's the power rule. F g prime of x is equal to g of x times f prime of x plus f of x times g prime of x. That's just restating the product rule. So f times g of prime of 3, which is what we're looking for, is going to be g at 3 times f prime at 3 plus f of 3 times g prime. So we're just substituting 3 in for the x. Now, do I know all of those things on the right-hand side of the equation? F of 3 is 4, g of 3 is 2, f prime of 3 is negative 6, and g prime of 3 is 5. What we've done is we've opened up a lot of difficult ones where we don't, like this next question, I don't really want to multiply a 3 or trinomial times 2 binomial. Okay. Like both of these guys, we could have multiplied them out. They're not terrible. What we did here was we avoided that step by applying the product. Okay. Now, if I have something to the effect of x plus 2 times x minus 1 times x plus 4 times x squared minus 8 times, I really have no desire to multiply those guys up. Is it a pain in the butt to do using the product rule? Yes. But is it less of a pain in the butt to do with the product rule than to multiply them out first and then do the power rule? Actually, yes. And so, terminology here, the normal line at a point P is one that passes through the point P and is perpendicular to the tangent line to the curve at P. So here's our curve. If that's our normal, or if that's our tangent line, our normal line is perpendicular to that. So what do we know about slopes of perpendicular lines? What do they involve? Sorry? Negative reciprocal. So this problem is no different. I've got a bit of an ugly question here. We have a trinomial times a binomial, which again, we could multiply out. Let's not. Okay. And again, this definitely comes in if you've got something like a function, square root of x minus 3 times the square root of 2x squared plus 8. You can't multiply those out. Okay. So you have to do the, well, actually have to do the chain law and the product law, but we'll talk about that later. And so we're looking for the equation of the normal line. So the first step would be find the slope of the tangent. So the slope is found by going f prime at -1. We'll talk about that in a minute, but we'll need to find f prime, the derivative of the function f. So f prime of x is equal to, we'll do x to the -2 times 2, or plus I should say, 2x to the -3 times the derivative, x cubed minus x minus, or plus 1, plus x cubed minus x plus 1 times the derivative of x to the -2 plus 2x to the -3. That's, again, me writing out what I need to do to figure this out. Derivative of that is 3x squared minus 1. And you have 2x to the -3 minus 6x to the -4. Now, to simplify this, if it was necessary to simplify this, I would have to multiply both of the expressions out. But anywhere in this question did I say find the derivative? No. What I'm trying to find is f at -1. So instead of simplifying, I'm just going to go f prime at -1 There's no way I'm supposed to stop it. -1 to the -2 is 1. -2, or sorry, -1 to the power of -3 is -1. So we have -2. This becomes 3 minus 1, so that's another 2. Plus -1 plus 1 plus 1 becomes 1. So -1 to the power of -3, I'm going to cube it, and then I'm going to drop it underneath. So this becomes -2, this term here, and then -1 to the power of -4 is -4 is +1, so this becomes -6. Thank you. -2, -1 cubed is -1. I've got to change that. So we have -2 plus -4, and the answer is -6. So the slope at -1 of the line tangent to the curve is -6. The slope of the normal line is opposite 1/6. So now it's just to find the equation of the line. y plus 1 over x plus 1. I'm just going to make sure I got that y value correct. Yep. Equal to 1/6. There's your slope y-intercept form. Right, so I put in y minus -1. Yeah. Okay. And then, so we have x minus 6y minus 5 equal to 0. Y is your standard form. Thank you. Hey, you've got to stop giggling on it. Who's fighting? Cousins?
No, I've never known people.
Cousins. Can you do question number 1E for me, please?
Okay.
Page 92.
One.
You said 1E?